Anything with a temperature emits light. It is one of the most basic rules of the universe. If you look at our solar system through a thermal lens, planets like Earth, Mars, and Venus all emit a soft, predictable infrared glow based entirely on how much heat they hold. But look at this diagram of the electromagnetic spectrum. If we shift our view from the thermal infrared imaging zone all the way down into the radio waves region, specifically the shortwave band between 10 and 40 megahertz, the thermal glow of the planets drops away. Instead, Jupiter alone shines with an intensity that rivals solar flares. That whooshing, crackling sound is an S-burst. It is the actual audio footprint of a massive electrical storm raging around the gas giant. Picking up that broadcast doesn't require a billion-dollar NASA satellite dish. Anyone can capture it using a cheap software-defined radio and a simple kit called Radio Jove. The antenna needed to grab this signal out of the sky is remarkably basic. You just need 2 pieces of standard copper wire, each cut to about 7 meters long, strung up horizontally between a couple of trees in a normal backyard. So how exactly is a planet hundreds of millions of miles away acting like a localized radio station, raining static right down into our neighborhoods? That signal is not generated by heat. It is non-thermal radiation, a type of energy produced specifically when electric charges are forced to accelerate. To get that kind of acceleration, you need a very particular environment. Jupiter has a massive, rapidly spinning magnetic field that stretches millions of miles out into deep space. Orbiting deep within that field is Jupiter's moon, Io. Io is violently volcanic, constantly spewing out gases that are quickly stripped down into a plasma of free electrically charged particles. As Io plows through the planet's magnetic field, the physical friction of its orbit acts like an immense electrical generator. The physics governing this interaction rely on the Lorentz force. Essentially, Jupiter's immense magnetic field violently sweeps up the electrons shed by Io's volcanoes. Because electrons are blocked from traveling straight across the magnetic field lines, they're forced into a spiraling corkscrew trajectory toward the poles. This continuous change in direction is a form of continuous acceleration. Accelerating this rapidly causes them to shed energy, emitting electromagnetic radio waves. Millions of these electrons are spiraling in perfect synchronization. Through a process called a cyclotron-maser instability, they amplify each other's emissions, combining their individual signals to blast a massive, cohesive radio wave out into the solar system. That broadcast produces a wave about 15 meters long. It shoots out from Jupiter, crosses the vacuum of interplanetary space, and pierces Earth's night sky. A tiny fraction of that massive wave eventually washes over the thin copper wire strung up in the backyard. Look at this diagram of an antenna. The incoming wave's oscillating electric field, marked by the arrows labeled E, pushes free electrons in the copper wire back and forth, creating an alternating current oscillating in rhythm with the Jupiter storm. That newly created electrical current travels down the antenna wire and into the receiver, where it is amplified and fed into an audio speaker. Inside the speaker, the current drives a magnet. That magnet rapidly pushes and pulls the speaker cone, moving the air in the room to recreate the static you hear. Listening to Jupiter means the friction of a volcanic moon millions of miles away generated an electromagnetic wave strong enough to cross the solar system, grab the electrons in a piece of backyard wire, and physically vibrate the air against your eardrums.